Hello everyone. In this chapter, we will continue our discussion of TCPIP Internetworking. So we will continue our discussion on layer 3 and layer 4 of the internet, which are mostly about TCPIP, UDP. And that's what we talked about last chapter, focusing on the standards and the protocols. So in this chapter, we are going to talk more about how we manage the internet and also how we secure the internet. So the first topic we're going to talk about is IP subnetting. So companies usually are given network paths by the ISP or an Internet Number Authority. So you are given the network path. Remember we talked about in the previous chapter, like the IP address. If you think about IP version 4, then maybe the first 16 bits would be your network path that are given to you. And then sometimes your network path will be longer, right? That means you have fewer IP addresses given to you, that may be 20 or even longer, right? So that's the network path given to you. Then as a company, then you can divide the remaining bits between the subnet path and the host path. So larger subnet paths means more subnets, but this results in smaller host paths, which means fewer hosts per subnet, because in total you only have 32 bits. If you have a larger subnet path, then you have fewer hosts, right? Fewer bits for the host. And the reverse is also true. For example, if a path has n bits, then you can represent 2 to the power n minus 2 subnets or hosts per subnet. So 2 to the power n, because you have n bits, right? So that's the possible combinations when you have n bits, is 2 to the power n. So we do the minus 2 because you cannot have a path that is all zeros or all ones, because they are reserved for other purposes. Right. So for example, with your host path, you have like 4 bits. Then the possible combination is actually 16. But then minus 2, then you have 14 possible hosts that you can represent. Now, of course, when it's 12, then it's 2 to the power 12, which is 4096. Then the number of available hosts will be 4094. So what happens if you have 8 bits or 10 bits? So for 8 bits, then 2 to the power 8 is 256. Then when you do minus 2, then this will be 254. And then if you have 10 bits for the host path, that means you have 2 to the power 10 combinations. That's 1024. If you do minus 2, then that's 1022. So in IP version 4, then we will think about subnetting. As we said, the total that you are given for an IP address, like in version 4, is 32 bits. Then the network path is assigned to you already. Like, so for example, all the Hong Kong U say networks started, I think the network path of Hong Kong U is something like 147.8, right? So that's the network path assigned to an organization. So of course nowadays it's more difficult for you to get a large network path like this, right? Because we are running out of IP addresses. So you may be getting a smaller network path. Also, it depends on the size of your organization, right? Then you'll be given different network paths, right, assigned to you. So suppose in your case, in this example, you have 16 bits assigned to you. Then the remaining 16 bits are free for you to decide what to do with that, right? So you can divide these 16 bits into a subnet path and a host path. So you can decide, for example, I want 8 bits for the subnet path and 8 bits for the host path. Then what will happen is that you have 2 to the power 8 minus 2. That is 254 possible subnets. And then you have 254 possible hosts per subnet. Right? So each part has 8 bits. So that's the firm's decision. So you can decide whether you want to choose this, or you can choose other combination, which we'll see in the next slide. Suppose instead of 8, I want to have a division of 6 and 10. So I have 6 bits per subnet, 6 bits for the subnet path, and then 10 bits for the host path. Then the number of possible subnet is smaller, is 62. And then the number of possible hosts per subnet is larger, is 1022. So again, this one is the firm's decision, you can decide. But a lot of times in either case, you will be wasting some spaces, right? Just wasting some IP addresses. For example, here in this case, if you know you don't have so many subnets, you won't have 200 subnets. Then what you will be doing is you have smaller paths for the subnets, right? You only have 62 possible subnets, and for each subnet you can have 1000 hosts, but it's not likely that you can have really 1000 hosts for every subnet, right? You may have some subnets that are very large that have many hosts, but then you may have some subnets that are smaller that may be using just maybe 100 200 hosts, right? So when situations like this happen, then you'll be wasting space. But as we said, no matter how you divide this part, you'll be wasting some IP addresses somehow. So suppose your network part given to you is 8-bit only. So that means you have a lot of IP addresses that you can play with. So suppose in this example, then I divide the subnet. I basically give 12 bits to the subnet part and 12 bits to the host part. Then what you can have is you have 4094 possible subnets and 4094 possible hosts per subnet. So another thing that you can also do is I can have 8 bits for the subnet and 16 bits for the host. Then you will have 254 possible subnets and 65,000 possible hosts. So let's look at this exercise. So if you have 20 bits assigned to your organization, then that means you only have 12 bits that you can assign. So suppose you select 4 bits for your subnet part. Then how many bits you have for the host part? So that would be 8, right? Because that's 12 minus 4. So you have 8 bits for your host part. So number of possible subnet, then it will be 2 to the power 4. 16 minus 2, that's 14. And this one, the number of possible hosts, it will be 2 to the power 8 minus 2, so that will be 254. Another exercise, so you are also given 12 bits, and then you use 6 bits for the subnet part. Then that means you have the remaining 6 bits for the host part. And the number of possible subnet is 2 to the power 6. So that would be 64 minus 2, that will be 62. And number of possible hosts per subnet is also 62. So next we will talk about network address translation, NAT. So the network address translation actually is supposed to send packets with false external source IP addresses and port numbers that are different from internal source IP addresses and port numbers. So when you use this, you can expand the number of IP addresses inside the firm. And then people also use this for security purposes because you can hide your internal IP addresses from the external sources. So this diagram is showing the net operation. So suppose you have a net firewall like this, then your client, you are using an internal IP address 192.168.5.7. So by the way, like those are IP address in IPv4, like starting with 192.168 are reserved for internal IP addresses. So I'm sending from this IP address and my port number is 3333, for example, that I'm sending out this packet. Then the net firewall will put the real source IP address and also the port number in a table like this. So in the translation table. So this is the internal IP address. And then this net firewall will translate to the with a false source IP address and port number. So suppose this one is 60.5.9.8. So it's one IP addresses that are assigned to this organization. So there's one possible IP address I can use. So the net firewall is going to send this packet with this false IP address, and also with another port number. And then this number will be added to the translation table such that I know like these two are actually the same thing. Then the net firewall will reverse the process for incoming packets. So when there's an incoming packet, like from another host on the internet, then coming back to this net firewall, then I will do the reverse translation. So this external IP address will be translated to this internal IP address such that I will know where to send this packet to. So when you do this, even if you have a sniffer listening to your traffic, this sniffer will not know your actual IP address. Right, so this one is the internal IP address. So net is transparent to internal and external hosts. So the net firewall will do all the work. Neither the internal host or the external host knows that net is taking place. So actually there is no need to modify how the hosts work. So there are some security reasons for using net. So external attackers can put sniffers outside the corporation, right? So they can actually know like where your packets are coming from, right? If you do not use net. So the sniffer can read the IP addresses and port numbers, right? And the attackers can send attacks to these addresses and port numbers. For example, if you are using net, then it's quite easy for external hackers to know what is the exact IP address and port number, say for your database server or for your web server. So they will know exactly which one is pointing to which. Then when you are using this kind of actual IP addresses, then it's very easy for attackers to send their attacks. Right? But if you are using net, then attackers learn only the false external IP addresses. So they will not be able to use this information to attack the internal host because your false external IP addresses can also be changed very frequently. So another reason for using net is you can expand the number of available IP addresses. So companies may receive a limited number of IP addresses from their ISPs, right? You may only be given a very small range of IP addresses that you can use. On the other hand, there are roughly 4,000 possible ephemeral, that's kind of like temporary port numbers for each client address. So for each IP address, there can be actually up to about 4,000 external connections. So if a firm is given 254 IP addresses, right, or sometimes it's like within one subnet, right, within a department in an organization, you are only given one subnet with 8 bits, then you only have 254 IP addresses. Then actually there can be roughly 1 million external connections. You have 254 times 4,000, right? Then with the 1 million external connections, you can actually use net to share that with many hosts, because for each host normally you won't use 4,000 external connections at the same time. You might just use maybe say 100, and that's a lot already. So say if each internal device averages several simultaneous external connections, each one will require a different port number. However, there should not be a problem with these many possible external IP addresses and port numbers. So again, so as we said, so with these say 254 IP addresses in use, you can actually have more than 254 hosts within this network, because they won't be using several thousand connections at the same time. Right? So it's kind of similar to many of the home network that you may be using. For example, when you get a connection from your ISP, your internet service provider, they may give you an IP address, like maybe just one, right? Then for your whole connection. But then let's say within your home, right? Then you have several devices, right? You can have your router, right? You have your wireless router, and that actually is doing something like this, right? You have your this one IP address actually is shared by multiple devices within your network, right? So that's how you can use one IP addresses for more than one device. So with net is actually similar to that. You can actually do this when you have many devices, but you don't have enough IP addresses. So companies often use private IP addresses internally. This can be used only within companies, never on the internet. And there are 3 private IP address ranges. One is like 10.x.x.x. So everything starting with this actually are private IP addresses. So the other one is 172.16.x.x through 172.31.x.x. So this one actually is not very popular because it is actually not stopping at the 8-bit boundary, so people sometimes get confused very easily. So I would say this one is not used a lot. And the most popular one actually is this one, 192.168.x.x. Yeah, somehow this one is the most popular. So many of the net firewall or your like wireless router setting will be using this set of IP address ranges. But of course, you can also set it yourself in your your wireless router administrator page. You can also set, I don't want to use 192.168, I want to use 10.x.x for my internal devices. That's also fine. So there are some protocol problems caused by NAT. Some applications like IPsec, voice over IP, and other applications may have a difficult time with net firewall traversal. So some of these applications actually must know the real IP address and port number of the host on the other side of the net firewall based on their protocol requirement. Then if they are not known, then actually they find it difficult for these applications to work well. So there are some net firewall traversal techniques, but they must be managed carefully. So that's why when you are using net, like sometimes you will find some of these applications may not work very well. Then you have to configure them correctly such that they can work. So just something that we need to pay attention to. So next we will talk about the domain name system, DNS. So a domain is any group of resources, like could be routers, single networks, hosts, etc., under the control of an organization. So the domain name system DNS lookup actually works in the following way. So for example, I'm using my browser, I'm typing in www.google.com or another host name like this one, dekin.pucanio.com. Then I actually need to find the exact IP address such that I can send a message there, right? So what I need to do is I will ask my local DNS server. So suppose here this computer is at hawaii.edu. I will ask my DNS server whether you know the IP address of this address. And then the hawaii.edu DNS server may have this information, right, or may not. If this server does not have the information, then you will forward the DNS request to the authoritative DNS server for this pucanio.com. So you will find who is the server for this, who is the authoritative server for this, and then so you will actually ask this server. And so if this server that has the information, then you will send it back. So this DNS will respond, will say the IP address is 60.32.6.87. So it send the response to the DNS server. So not the client host, it will send it back to the DNS server. And the DNS server will send the response back to the host, and then it will also store this address. So next time it will not know it does not have to ask again. So the DNS really is a general naming system for the internet. And a domain is a set of resources under the control of an organization, and there is a hierarchy of domains. So the top level domain names are like .edu, .net, .org, .com. So these are the very common ones that have been here since the very beginning. And then you can also have country level domain names like UK, so I think it's Netherlands and Ireland and Australia and so on. So you can have actually different top level domain names that are based on these very common ones or the countries. Of course, in recent years there are also some other domain names that we are seeing. So the root is all domains. There are 13 DNS root servers. And there are two kinds of top-level domains, like generic top-level domains indicate organization type, like .com, commercial, like .edu, education.gov, and so on. And country level, as we have mentioned, these are also specific to countries or region. Traditionally, generic top-level domains were strongly limited in number. So there have been a few additions over the year, like .museum, .name, .codes. So traditionally, I think before like 2012, like this kind of top level domain name was still very limited. But then after 2012, actually they changed the rules. So any individual or company actually can propose to administer a generic top level domain name. So now actually has become more diverse. There are other domain names that people can apply and use. But of course, in general, we know like the very popular one like .com, .edu, .gov are still the most popular because people actually remember those more easily, right? People have been used to this kind of naming. So for some of the newer names, some people are using, but they are not that popular yet. Companies usually want second level domain names, like because in the past 30-40 years, people already know like they should get the something like Microsoft.com, Apple.com, Pango.com, etc. Because like that's kind of what people will think about when I think about a company. I will very generally say Microsoft.com, right? Apple.com, IBM.com. So we know this .com is actually very important. So that's why a lot of companies actually make sure that they need to get all these names such that people will not go to another wrong website. So competition for these names is actually fierce. So many of these domain names actually, if you register early, like many years ago, and actually you could sell some of these domain names at very high prices, even like more than $1 million US, right? In some cases, if you get very good domain names that some large companies want. So most companies further divide their organizations into subdomains or subnets. For example, Hawaii.edu, then you can further divide into different colleges, different faculties like Schindler.hawaii.edu. And this subnet, you can actually also use the host name, right? So you can actually have a specific URL or have an kind of address like this for each of your hosts, right? As long as you have all this in your DNS, then people can find you using this name. So at the bottom of the hierarchy are individual hosts. So usually these are pointing to the web server, or of course sometimes it's not a web server, it could be a database server or other server, right? So it is pointing to the individual host. Now of course a lot of times for websites you'll be seeing www dot something. So in the beginning this www then of course referring to World Wide Web. That is actually also pointing to an individual host, which is your web server. But then of course nowadays a lot of times people may skip the www, right? If you set it correctly in your DNS, that will also be fine. So next we'll talk about the simple network management protocol. So we have actually talked about the simple network management protocol, the SNMP from chapter 4. We know we have a manager program that can manage all the different devices, which are called the managed device. And then you also have agents. These are software that are running on the managed devices that actually will communicate with the manager on behalf of the managed device. So as you said, the manager actually will store all the information about the devices in a management information database. So we call it the MIB. So it store the retrieve information. So MIB can refer to either the database on the manager or sometimes to the database schema. So we have also talked about like messages that the manager can send to the device, and the device can also send messages back to the manager. So the manager actually can send commands that can be get commands or set commands. So get command is to get information from the agent, and set command is to tell the agent to change the value of some of the information or some of the parameters or some of the settings, or you can actually use it to change how the managed device is operating. And then the responses are actually sent from the agent to the manager, sending back to the information requested by the manager or sending an acknowledgement. The managed device can also send a message called trap to the manager. So these are basically the alarms sent by the agents. So SNMP actually use UDP as a transport layer to minimize the burden on the network. So because there are many of these messages sent between the manager and the agent, so if they are using TCP, that will generate a lot of overhead. So that's why SNMP is designed to use UDP to minimize the network traffic. So get command is used to get the information, and as we said, set command is actually used to change some of the parameters of your managed device. So actually, set commands can be very dangerous if used by the attackers. That means the attackers can change anything on your devices, so they can actually change your blacklist, change your settings. So as long as they change some of the settings on your device, then your network is very vulnerable. So many firms actually disable the set commands in order to stop such attacks. However, if you disable these set commands, you basically are giving up the ability to manage remote resources without travel. So you have to go to the device physically in order to do some of this setting. So there are also like different versions of this SNMP. So SNMP version 1, basically community string is shared by the manager and all devices. So the community string basically is just kind of like a password. It's actually used by the manager and all devices. Now, of course, if you think about it, this kind of security is actually quite poor, right? Then if we use SNMP version 3, then each manager agent pair actually has a different password. Then this is much better security, right? So when you have this, then actually the security will be much better and your network is less vulnerable. So there are also something called objects in the SNMP. So objects are actually specific pieces of information. So it's also the number of rows in the routing table, for example. It can also be the number of discards used by lack of resources. That may be indicating a need for an upgrade. Right? So sometimes people get confused thinking that the objects in SNMP are the managed device. Actually, the objects are not the devices. Objects are basically specific pieces of information about a device. So for example, you have a router XYZ. So the router is not called an object, it's kind of called a system. And for this system, then you have different objects. So you have system objects. So these are like one per system. So you have a system name, system uptime, since last reboot, and so on. So you have different kind of properties of this system, right? So in kind of other terms it's like properties, but in SNMP we call this the objects, right? And then you also have IP objects, right? And also there's TCP objects, UDP object, and so on. So that means you have kind of like one protocol, one object for each protocol for each system. So then this object will be storing all the information related to that protocol. For example, IP objects, then is storing about the forwarding, the number of row discards, the number of errors, and so on in this IP object. And then there are also interface objects. So there is one per interface. That means the port. Right? The router has many ports, right? So for router we call them the interface. Right? And for each interface, then we have the speed, we have the up down, testing, and so on. So the different status of the interface. Then all these are actually called the objects under the system. So that's kind of how you name this information in your in SNMP, and also they follow this hierarchy. So SNMP manager program collects data and store them in the MIB, And of course, after storing, then you need a way to see the data. So usually then you will have some visualization program. So that is the administrator's interface to the MIB. So it will be showing your network status and also the statuses of your device as a graph, right, dynamically. So it will help the administrator visualize patterns in MIB data. You can also use this program to order the SNMP manager to collect certain data or to send out certain set commands to change the configurations of managed devices. So this was basically normally there is an application visualization program that you can use to visualize all this data and also to manage all your devices. So these different visualization programs or network management programs actually will have different user functionalities like reports, diagnostic tools, and so on. Now, of course, these tools are very important. You need to generate daily or weekly or monthly report, right? These functionalities actually are not built into the standard. So the standard only specify how you can do getting, setting, how you can set alerts, how you ensure security and so on, but it actually does not, the standard does not specify how you are going to visualize the data. So this is actually up to the network visualization program developers to design. So that's why when you have this, you actually have many different network visualization programs available. So the selection of a good network management program or vendor is actually very important in your network management administration process. Next, we'll talk about IT security, or what we call IPsec. So we know virtual private networks, we have talked about it several times in previous chapters. So basically, is cryptographically protecting the communication over an untrusted network. Because when you send something on the internet or when you send something on a wireless network, right, they basically can be easily seen or sniffed by other people. So virtual private networks basically is, I want to make sure all this information is encrypted such that when the information is on the public network, even people can get the data, they will not be able to decrypt it. So it's basically private in the sense that no one else can see the contents, but it still travel on the public network. So we already talked about like host-to-host VPNs in chapters 3 and 7. So we are saying it's private network, but again, it's encrypted, but part of it is still on the public network. So there are two types of VPN. So it's like remote access VPNs, connect a remote user to a corporate site. The user then connects to a VPN gateway at the site. So this is very common for many organizations nowadays. For example, if you are doing work from home, right, and then you try to connect to your computer server in the company, and then the traffic actually is going on the internet, then there may be some confidential information there. So if you are using VPN, then you make sure all the traffic between you and the company are encrypted. So that's a kind of remote access VPNs like this. Right, so you make sure like all these are encrypted such that when it travels on the internet, people cannot get the content. The second type of VPN is what we call a site-to-site VPN. So it's actually provide all traffic traveling between two sites. So each site has a gateway to encrypt outgoing traffic and decrypt incoming traffic. So it's kind of like this. So you have two sites, and then you have kind of the connection, and then you have the VPN gateway on both sides. So there is the IPsec VPNs, which is governed by the IPsec protocols. So it actually operates at the internet layer. So it protects the transport header, application content, and at least some of the IP header contents. And this protection is transparent. That means upper level content does not even know that it's being protected. So on the upper level application actually does not have to worry about this. So again, for this protection, actually it provides confidentiality, so the message will not be seen by others. Authentication, so you are talking to the person that you are supposed to be talking to. And there's message integrity, that means you ensure the content has not been tampered by other people. So IPsec has two modes of operating. So there's a transport mode and also the tunnel mode. So both are actually under IPsec, and each mode has strengths and weaknesses that we'll talk about very soon. So this one is the transport mode. In the transport mode, the IPsec provides protection over the internet and also over site networks between the hosts. So that means even within this organization's own network is protected. Right, so this one is called the transport mode. It's kind of like from host to host, right? So you have digital certificate and also configuration required on each host, such that you can have this at the host level, that it will be secure on the internet and also within your own company's network. So the transport mode requires a digital cert and configuration mode on each host, so this is relatively more expensive to execute. The other one is a tunnel mode. So in the tunnel mode, the IPsec actually only provides protection over the dangerous internet. But it's not encrypted within the site networks, right? So there's no security within the company network. You suppose the traffic here is safe. You only do the encryption or the security part actually on when the traffic is going through on the internet. So this one is the tunnel mode. So when you do the tunnel mode, you don't need to have digital certificate and configuration on every host. You only need to make sure you have the correct configuration on the gateway. Right? So when you do this, only the two IPsec gateways need digital cert and configuration work. So it's relatively cheaper to implement. So this is just a table comparing the two. Again, for the transport mode, you have better security because it provides host-to-host protection. But there's also a problem because firewalls cannot read the encrypted traffic. So sometimes, like some of your users or employees are actually not following your rules. They are downloading something that are actually containing virus. But then if it's also encrypted, then actually you cannot check it at your gateway. And then the tunnel mode actually is not as good because it only provides security over the internet or another trusted network. But of course, the good thing is the firewall actually can work. And in terms of the cost, the transport mode is higher because of the configuration work on each host. And then for the tunnel mode, the cost of course is lower because IPsec operates only on the IPsec gateway. So now we'll talk a little bit about something called the Security Association. So an IPsec Security Association is actually an agreement between two parties. So this agreement is about what security methods and options that should be used during the communication. So for example, in this diagram, we have two hosts here, Sal and Jen. So first, Sal will send to Jen the Security Association for transmission. And then the second step, Jen will also send it to Sal what security association should be used. And this security association for transmission actually can be different from the one here. So you can actually have two different ways of sending messages, like when you are sending a message in the two different directions. And then the IPsec policy servers actually allow centralized control. It can specify what security associations will be allowable for each type of communication. So you have an IPsec policy server that will be storing a list of allowable security associations. Right, so it will be storing all these, that will be easier to manage. So it's just a quick comparison of IPsec versus a SSL TLS VPNs. So the IPsec VPNs of course is actually handled by IETF, and the SSL TSL originally also created by Netscape as SSL, and then later on is renamed TLS by IETF. So basically both of them are under the management of IETF, but then they are actually at different layers. So IPsec is actually working mostly at layer 3, and SSL TLS are working on layer 4. And IPsec actually is not built into browser, web servers, and mail servers, right? But it's actually built into browsers, right? For SSL is built into browsers, web servers, mail servers, and so on, because it has been used a lot before IPsec was actually well developed. So that's why it's very convenient. Like when you go to websites, when you use HTTPS, it's already giving you the protection through SSL TLS, and you don't need to worry about establishing another actual VPN there, right? So it's very convenient for you to use SSL TLS in many of the existing applications. And then on the other hand, IPsec actually can protect any application. So you can protect any application. You can also protect transport layer header and some of the IP header, because once you basically establish a VPN connection, say with another host, basically you'll be protecting all the traffic. But then you will compare that with SSL TLS, that actually that only SSL TLS aware applications such as web and some of the email clients will actually be supporting this. But then otherwise, you will not be having this kind of protection. So it only protects specific applications. And then IPsec actually support different types of VPNs, including like host to host, remote site access, and also site to site, as we have seen. And then SSL TLS actually only support host to host, just again like HTTPS. So the strength of security of IPsec actually is better than SSL TLS. Again, SSL TLS is a little bit older standard. IPsec is newer, so it has stronger security, it has better consideration of many aspects, and also it has better protection of the different headers. And also, like IPsec can allow this centrally managed security, where SSL TLS does not support that. So this table basically compare the IPsec and SSL TLS. So IPsec provides security to application content transparently. It's also making the protection automatic. However, this also means that the application cannot tell whether it's being protected or not. So a lot of times the application designer still requires SSL TLS in order to be sure that it's being protected. Again, it's like HTTPS. Like even though you say you are making your connection using VPN, like all the traffic are being protected, but actually I'm not sure, because the application actually does not know it. So I will still require you to use, for example, HTTPS instead of HTTP, like when you are making this connection. So that's why IPsec itself is still not enough in a lot of cases. You still need to use it together with SSL TLS for specific applications. So next we'll talk about IP6 management. So we are currently dealing with the transition from IP4 to IP6. Then of course in IP6 we still have the similar issue of subnetting, and then we also need to do IP6 configuration. Also there are other new IP6 standards like extending DNS and so on that we need to deal with. So initially devices only had an IP4 protocol stack, right? Like this diagram here, you have the application layer, transport layer, then at the internet layer, you only need to deal with IP4. Then nowadays, many devices actually are like this. At the internet layer, then you need to deal with both IP4 or IP6. So the IETF assumed that vendors would create dual stack products such that IP4 and IP6 are both supported, and hope that IP4 will gradually fade away. Although it doesn't seem to be fading away now, it's still actually a lot of traffic on the internet are still on IP4, but at least we have a lot of new devices that are running on IP6 only, so we will see how that goes. So as we know, we have run out of IP4 addresses. So many new devices now only have IP6 addresses, so only have an IP6 protocol stack. So if the devices can only run IP6, then actually it will not work with old devices that can only support IP4. So company must re-engineer their networks to support IP6 only clients. So that means some of the routers or hubs that are too old that do not support IP4 cannot be used anymore. So the network devices must also deal with the global IP6 unicast addresses. So they are just like public IP6 addresses, but they have three parts but different names. So like IP4, we have the network part, subnet part, and host part that we talked about earlier in this chapter and the last chapter. So in total, it's 32 bits, right? And for IP6, you have the routing prefix, and then you have the subnet ID, and then there's an interface ID, and so these are just the different names, and then the total is 128 bits. Right? So basically, the routing prefix is just like network part. Subnet ID is just subnet part. Interface ID is basically the host part, but in IP6 we call them different names, right? And then as we have learned in last chapter, and also earlier this chapter, like in IP4, the length of these three parts are actually variable, right? But we only make sure that the total is 32 bits. But for IP6, then the path length for the host part is always fixed. The host part is always 64 bits, and then the subnet part and the network part are variable. Okay, so the total will be 128 bits. So that's kind of the difference here. Like the host part is always 64 bits here, so it's fixed. So the global routing prefix here, as we say, is kind of like the network part in IPv4, so it's the beginning part of the IP6 address, and the subnet ID is the subnet part, and the last part here actually is the interface ID, which is the host part in the IP4, and this one is always 64 bits. So it's almost always, so there are some exceptions, but let's just assume it's always for 64 bits here. So it's not of variable length like IP4 host part. So it's actually wasting 64 bits, like in some sense, right? Because like you won't have like 2 to the power 64 different hosts in the same subnet at the same time, right? Chances are you only have very few hosts, maybe even if you have a lot, maybe just have thousands of hosts within one subnet, but you won't have this like 2 to the power 64 hosts right there. So basically when you are using IP6 is used like this, we are actually wasting a lot of bits, right? We are kind of wasting 64 bits, but somehow when they design IP6 address, they think that this one is okay, so they are wasting a lot of bits here. They still have 2 to the power 64 bits here, right, that they can use for the network part and the subnet part, and they think that's enough for handing out to like all the organizations and so on. So anyway, that's how they design IP6. So that means theoretically we say we can use 2 to the power 128 IP addresses in IP6, but in practice actually we are wasting a lot of that. We are already wasting 2 to the power 64 like bits for each of them, so we are actually wasting a lot of these space. But anyway, so that's how it was designed. So as I said, like, so the first two parts here, the total will be 64 bits, the network part and the subnet part. Okay, and then so what is the 64-bit about? So it's actually the kind of modified 64-bit extended unique identifier format. So remember we talked about the EUI48 addresses in earlier chapter. That's the MAC address. So basically this 64 bits comes from your MAC address. So it's actually display the EUI48 address in hexadecimal notation. So first you make into hexadecimal, you convert to lowercase, you remove the dashes, so it looks like this, right? So that's your EUI48 address. And the next thing you do is you add FFFE in the middle. So you add in the middle, so it becomes like this, right? And then the third thing that you change is in the second nibble. So in this case, a D here. Again, nibble is a group of 4 bits. So 1101. So what you do is you invert the second bit from the right. So you invert this bit. If it's 0, you flip it to 1. If it is 1, you flip it to 0. Right? Then you can change it back to the hexadecimal notation. In this case, it will become F. So this is called a modified 64-bit EUI. So again, that's kind of because of the design of IP6, that's what is needed. So you flip this bit, and this will become kind of the second part of your IPv6 address. So just a quick recap. So you begin with your EUI48 address in hexadecimal notation. You remove the dashes and make them into lowercase. Then you divide the 48 bits into 2 halves of 24 bits. And then you insert FFFE between the 2 halves. And then you place in 4 hash groups separated by colons. And then finally you flip the second least significant bit in the first octet. So that's why you modify it. So that's why we call it the modified address. So there are other IP6 standards that we need to pay attention to. So for example, the DNS. So the DNS information for a host is contained in several records. So originally it's just like for IP4, it's just a DNS A record. So the A record contains the IP4 address for the target host name. And then for IP6, we call it the DNS AAAA record. So a new address record had to be added for each host name, like if it has an IP6 address. So IP6 addresses are 4 times as long as IP4 addresses. So the added record is called the AAAA record, or the 4A's record. So finally, we'll talk about some of the other TCP/IP supervisory standards. So one thing is about the dynamic routing protocols. So how do routers get their routing table? So we talked about the routing tables in the last chapter, but how do routers get these tables? So basically the routers constantly exchange information. So the communication must be standardized by a protocol, and in this case, the one called the dynamic routing protocol. So there are several dynamic routing protocols, so where they can exchange their routing table information. So note that routing means 2 things in TCP/IP. So as I said, when we route a packet, so we call it routing. So it's the process of forwarding an incoming packet. And sometimes it can also mean the process of exchanging routing table information through the dynamic routing protocols. So again, this one is kind of some of the casual nature of IETF, so making this kind of naming sometimes a little bit ambiguous. But anyway, normally when we say routing, we are talking about routing a packet, but it's also about exchanging routing table information. So suppose you have this organization network, and then within your organization network, you may have several internal routers. And then when you are going out of your organization network, then you have what we call the border router. Then this border router may be connected to your ISP or other external networks, like through another border router. Then actually when we are having a diagram like this, different dynamic routing protocols may be used at different levels. For example, like for internal routers, usually the protocol used is called the OSPF or the EIGRP. So these are the interior dynamic routing protocols. And for exterior dynamic routing protocol, then usually there's one standard called the BGP. So the OSFP, the open shortest path first, is actually good for interior routing protocol exchange. So it's for large autonomous systems that use only TCP/IP. So it's actually used for systems that rely on TCP/IP only. And there is actually another one called the EIGRP, it's an enhanced interior gateway routing protocol. So it's actually a proprietary system protocol by Cisco system. Cisco is basically one of the largest vendors for all these networking devices. So it's not limited to TCP/IP routing, but it can also handle other system or other protocols like IPX, SPX, SNA, and so on. So it's also used quite a lot in many of these Cisco systems. Then for border routers, usually another protocol is used, so it's called the BGP, the Border Gateway Protocol. So it's an exterior routing protocol. So of course, like organization cannot choose what exterior routing protocol will be used, right? Normally for an organization, you choose what you use internally, like as the network administrator, then you decide what you can use internally, but then externally then is usually decided by the ISP, right? And because of the scale of the routing and also kind of the complexity of the external network, then the interior routing protocol actually is not appropriate. So we will need to use the exterior routing protocol that is different. So in this case, the most common one is called this the BGP. So another thing we want to talk about is the ICMP. So it's actually used to handle supervisory communication between internet layer processes on different hosts or routers. So it also avoids making IP handle this type of message. So it's standardized by the internal control message protocol. So when you have some supervisory communication that are like the messages that are for like administration or what we call supervisory, and so these are not actual user packets that you want to send. These are like for the administration operations of the internet. So we actually use a separate protocol to handle these messages. So it's called the ICMP. So for example, like the ICMP error message can be sent to like when the router is detecting an error, I'll say host unreachable, and then sending a message back to the host. Then this one is called this one is being sent over ICMP. So ICMP actually provides error advisement messages. So it can also help in the diagnosis of errors, and although it's doing that, it does not bring reliability. So it's saying that it's error, but it's not actually asking any resending and so on. So another example use of the ICMP is the ping command. So when you type a ping command on your computer, you will send a message to the destination IP address, and then the destination host will reply a message saying that I'm available, and also it will tell you the round trip latency. Right? So a lot of times people use the ping command to check whether a server is up running or not. So basically the ping tells the pinger that the ping key is available. It will also give the round trip latency. So these messages are sent on ICMP. So an ICMP message is encapsulated in the data field of an IP packet. So the source IP address reveals the IP address of the transmitting device. So this one actually is a possible security violation, so we need to be careful about this.